This is one of the dry bags that when you like actually roll it, but it's huge. Or if I like, it just looks like you can sit and I don't have a designated locker. I have to pay for a locker or use a living room. But and this is like a great adventure. Hiking with it. Not fully compatible with like full-on backpack. Unless someone else. Oh, thank you. It would have been a great day. So do we know Molly got approval for recording? Like a minor code. No, I'm gonna turn in my assignment.
Sure.
But not for this section. Like, very different than that.
Okay. Sorry. You said it like on the
So much. I also still have one. Are they gonna? Like review? Is that something?
Oh,
I mean, this was like one side.
Yeah.
I know.
is there anyone who brought their problem set 7? I can give you the answer keys.
I think there's a stapler anywhere.
Alright, fine.
Okay, I'll just pull the corner or something.
We also.
Thank you so much.
Thank you. Mhm.
There's a set that's coming because it's great. I like really could have moved up with like low.
Leadership education and girl
I
development.
was like,
It's awesome. No, because Lauren is like that. She like is the person who created
excited to and then so my first section.
But look at this question, is what does leadership do to like all these
I
things?
would experience this kind of like a lot of like microaggressions with dollars.
Yeah.
Basically excluding women who were like CEO, like company.
I say something about like And so go back to the marriage, just we should have like work.
Yeah.
Have those conversations and
Oh,
I'm not sure they all love.
That's a good.
And also like, it turns out. So she just doesn't want to support us.
Finish the
Yeah.
paper for the
I-
class. It's very not good.
And I was, maybe the one who.
So don't.
Like,
I feel like it's actually worse than
talk to people around you about what they saw.
because they would look at
Because
lots of room for improvement.
yeah, and it might be and then I did let another friend read it.
That's what I was thinking about because
He, like, he was not so.
Yeah,
Like, what's going on, so it's fairly confident.
I like that.
I love that white man thing. I'm sorry.
Walk down to my.
This is an accurate representation of what the life I was in a meeting, I was in the yeah.
Yeah.
It turns out that
My spreadsheet. Yellow is good. Yellow is good. You get a broad.
I know.
And green is good. You get that. White is not that. And then some of them. And she said that she was my alternate. Right? Now everyone messaging me.
Oh, yeah, just see if it's good enough.
Yeah, I'm like, you should know if you're done. Like,
Yeah, well, they're probably like.
I'm like, yeah.
No,
just do this.
You're alone, but also like, no,
Yeah.
if you want also, I would.
What day is that?
Not successful.
Is there anyone who brought their PS7 with you? Officer 7?
Listen to me. I will kill you. Can you just tell me it was due today and maybe
No.
I was. And you're.
I do, I never do, it's probably have one pencil. I don't have.
In my office, we have 7 boxes of this small liquor, so I listen like
Which one? I do it all in the format.
Oh, okay, sure.
I was speaking,
Um,
I'm speaking as an effective bystander.
Okay. Good afternoon. Review session. So, thank you for your questions. I received a lot of questions. Just the questions alone were 5 12-point pages. And so I discovered that it was a lot easier last time when I had to make up half of the questions myself, thanking you profusely for it. This time, you send lots of questions, and I'm like, I'm going to organize this. But unfortunately, there's quite a bit of overlap in the questions, which is to say, 5 people asked for interpretation of logit, probit, and so forth. We'll definitely do that. And then everybody had sort of their idiosyncratic questions, and there was a limited amount of overlap. So I'll prioritize questions that overlap, that is, questions that were asked by more than one person, or questions that I thought should have been asked by more than one person. And then we'll go through the interpretation of logit. And I'll strip away most of the explanations and just tell you here are the 3 ways of basically doing this, and here's how they differ, why we would want to do this. Okay. Now I'm going to do this on the blackboard, and because this is a review session, you should interrupt, add, contradict, or misdirect me as you wish. Okay, so to be active. Right there.
I know that Molly is ill and like we want to be here, but
We're recording it already.
perfect. I was gonna ask
Thank
about
you.
voice memo.
Yeah, thank you. No, others are PAA, so we're doing that. And I think, hang on, let's see, so where are we recording? Okay, no further than here. And, oh, good. Excellent. Thank you. All right. Generalized least squares in HLM. The questions range from technical details to what the heck, why? So let's see about that. All right. So GLS and HLM, as we have covered them, are about the errors, about the individual level structural errors with the OLS assumption. Sorry? They're IID what? Huh? So they IID means identically and independently distributed. And how are they distributed? Normal. Okay. And what's the mean of this normal?
0.
0. Okay. And what is the assumed variance of these errors? It is a constant. That's right. So we have some sigma square in the errors. We're seeing they're all IID distributed like so. The reason OLS assumes that is that it makes statistical testing very straightforward for statisticians. Okay, so your t-tests, f-tests, and all that beautiful stuff was originally derived under the simplifying assumption that the errors are IID normal. In reality, especially in the social sciences, we're often not so lucky. So what are the three conditions? What are the three deviations from IID that we've worried about? What other error structures have we considered? Give me one, Anna.
Heteroscedastic.
Heteroscedasticity. Somebody else. What does heteroscedasticity mean?
The variance
Yes,
of errors.
Oh, sorry. Behind you. What's your name again?
Shu.
Shu.
The variance of the errors is consistent across
The range of
activities.
X. Okay, great. Okay, so if we have Y here, suppose we have a regression line, and maybe that our point cloud looks like this, right? So small errors here, huge errors there. Our point cloud could also look different. So perhaps this is the regression line, and our errors are like this. Okay, small in the beginning, huge in the middle, small in the end. And so here we have heteroscedasticity means that our errors, the variance of the errors differs across individuals. So how would we write the OLS errors with heteroscedasticity? Heteroscedasticity means that our errors are perhaps distributed to normal, which means 0, but an individual error variance. Okay, now we noted that we could write out the error variance covariance matrix capital sigma, sort of like so. Is that so? Okay, where this matrix, if you will, has individuals as the columns, as the rows, individuals as the columns, and each entry tells us how the errors of these two individuals covary. Now, the covariance between the errors of the first individual and the first individual are just the error variance for the first individual. And here for the last individual, it's the error variance of the last individual. Here then, we would have how the errors of the second individual covary with the errors of the first individual. Here, the covariance between the errors of the first and the second again. This is obviously going to be symmetric, and so forth. Now, in OLS, we're assuming that all the error variances on the main diagonal are a single number for every individual. Therefore, in OLS, we could write this huge error variance matrix just as the error variance that everybody shares times the identity matrix. That makes this so easy. Now, if we had pure heteroscedasticity, then all of these off-diagonal elements would be 0 because the errors don't correlate with each other. But the elements on the main diagonal would not all be the same. Good. Now, what happens if we have clustered data? If we have clustered data, it means that the errors of people in the same cluster are correlated. So with clustered data, you would have an error variance covariance matrix that's so-called block diagonal. All right, so here's the something like this. On the main diagonal, people within a cluster, people within a cluster, here person 1 and 2, each have their individual error variance. So that would mean that we have heteroscedasticity. And additionally, the errors correlate with each other. That's why the off diagonals are 0. Now, typically we assume that these clusters are disjunct. So suppose, yeah, so that means that each individual is only part of one cluster. If so, all the off diagonal elements are 0. 0, 0, 0. Everything here, 0. Okay. This would be a clustered error variance, covariance matrix. Now, yes, Frank.
I have a question just about what you just said, that in heteroscedasticity, that diagonal line, they are all the same,
Different. Homoscedasticity, same variance. All of this is one number. Heteroscedasticity, different variance, different values for the mean diagonal. Yes, please.
If we're talking about clustering, how come the elements on the off diagonal would be 0? I thought that they would be correlated with each other.
So here I've drawn a clustering matrix of a very particular type. Here I'm stating, this is information that the sociology gives you, not the stats. The sociology tells you that, say, you have kids distributed across different schools. Each cluster is a school. So we're assuming that the kids within a school interact with each other. Therefore, if you and I are in the same school, your and mine errors are uncorrelated. But if there's somebody else who's in a different school, then our errors will not be correlated. That's an assumption. And so, but if that assumption is true, then say, so if I'm person 1 and then there's person 3 that's in a different school, then here we'd be assuming that person 3's error does not correlate with mine.
between groups, they don't correlate, which is why it's,
Between, correct.
thank you,
However, that is a substantive assumption,
that makes sense.
okay? Because, so, hey, anybody can give me a story for why the errors of kids who are attending different schools might nonetheless be correlated? Yeah.
District funding, so if you're comparing different schools that are within the same district that have a certain set of funding, and then also comparing them to schools that are in different districts, then those schools that are in the same district might have certain correlations.
Good example, right? So these kid number 1 and kid number 3 may be in different schools, but they're in the same district, and hence they're exposed to all the shared shocks that everybody in the district is exposed to. Another example, yes, Anna?
Oh, just to clarify, so like on the whole, our data set is the heteroscedastic, but like within clusters, it's homoscedastic because they have the same variances.
No, it doesn't have to be like that. Usually when we assume that we have correlated errors within the cluster, we also generally permit that they're heteroscedastic within as well as across clusters. So here's another example for where you might have kids who are in the same, two kids who are in different schools but nonetheless have shared error terms. Well, maybe they're siblings. So they have a shared family component in their errors. There are lots of reasons why errors might be correlated. And you want a substantive handle on why they're correlated. Now, that brings us to GLS. In OLS, we've assumed that the errors are IID normal. Then we've computed our standard errors using that assumption. When the errors are not IID normal, the OLS standard error formula is wrong. The OLS standard errors may be too large, they may be too small, but they are going to be wrong. So what can we do? Well, we could go to generalized least squares. Generalized least squares simply builds the actual error variance covariance matrix into the estimator. And both for the slopes and for the standard errors. So what's the variance formula in matrix notation for the slope in the OLS regression? First, it's our variance times x prime x inverse. With a single x, that's the same as the error variance divided by n times the variance of x. So this is the formula for the variance of the OLS standard errors. GLS uses a different formula. GLS uses x prime sigma inverse x inverse. Okay. That's a different formula. Turns out to be the same if our errors are IID. Convince yourself of this. Okay. So if my errors are, sorry, something not clear? My writing's definitely not clear.
Yeah,
So
because we sigma hat, it takes multiple right? Estimated.
no, it's not sigma hat yet,
Oh.
but I like that you see that we're getting there. So with GLS, this is the formula for the standard errors. Now, if sigma, if my error variance covariance matrix really was sigma times the identity matrix, then we'd have x prime, the error variance sigma, inverse, times x inverse. So here we have inverse inverse. That means you can just pull out the sigma, the error variance, and what you've left is x prime x inverse. So under IID errors, these two are mathematically identical. Okay, but often we don't have IID errors, so we need to estimate this. Now what's the key problem? Why can't we just use this formula directly? You guys in the back.
Well, there are too many variables essentially for that is difficult or impossible to estimate unless you have some sort of punch, in which case it becomes FGLS, which is why they would then have sigma.
Oh, terrific. Okay, good. Moving on to the next question. So now, sorry, I'll repeat this, okay? Here, this sigma thing, this is unknown to you, and it has a gajillion parameters. In fact, right, so you can see here, we have n observations, but we have n rows and n columns. So we definitely have more than n free parameters in here. But if you have more parameters than observations, then you definitely cannot estimate all of these parameters. Therefore, you need to put structure on this matrix. That is, you need to make some assumptions about how these unknown parameters relate to each other. For example, in clustering, you might assume that all the elements that are outside of the cluster block are uncorrelated. In that case, you've now made a bunch of assumptions, namely that this is 0, this is 0, 0, 0, 0, 0, 0, 0, 0. So you don't need to estimate that stuff anymore. You only need to estimate the within cluster variances, and that may be feasible. So, all right. So after you've made assumptions about the structure of the error variance covariance matrix, you estimate the error variance covariance matrix. We give this a hat. And because this step is fraught with mistakes, you no longer call it GLS, you call it FGLS, feasible least squares. And why is it feasible? Well, because you've made a bunch of assumptions that allow you to estimate the error variance covariance matrix. So, compared to OLS, what's the advantage of GLS?
Are the standard errors more either like more efficient or they're more tight or making better assumptions about it?
The first two things were the same and they're correct.
Okay.
The GLS, the GLS standard errors are efficient, which means the tightest possible if you have non-IID errors. In addition, and that was your third point, they're also correct. OLS standard errors for non-IID errors are incorrect. They're just wrong.
To be fair, they're correct, given that the assumptions that we viewed in feasible GLS is correct, right?
That's why I asked about GLS versus OLS.
Oh, okay.
Yes.
Okay.
You're paying attention to the fine points. That's very good. Okay. So yes, in practice, you can only do feasible GLS. You need to estimate this thing. And then whether or not your GLS standard errors are correct depends on whether the assumptions you've made about the structure of this sigma matrix are correct. Now, under certain situations, we have really good theory for the structure of the sigma matrix. For example, if you have hierarchical data, suppose that you have a data set of students in 100 classrooms randomly pulled from all the classrooms in the nation. Then chances are that yes, all the kids within a given classroom know each other, but kids in different classrooms don't know each other because we've sampled classrooms from the entire nation. Right? A Wisconsin classroom, an Arkansas classroom, yeah, they're not going to know each other. Huh, terrific. Well, with that assumption, you can now estimate FGLS in your fund. So, that brings us to HLM. What's HLM? From a statistical perspective, HLM is just FGLS. Hierarchical linear models are linear models, so like OLS, to be used in situations when your errors are not IID. We typically use HLM in situations where we have a really good idea about the structure of our sigma matrix. Conversely, if you don't know how your data are nested within each other, then you can't use HLM because you can't, you have put no restrictions on your sigma matrix, and so it's super hard to estimate. So that's the first way I want you to look at HLM. It's just, a tricked out way of doing a linear model while getting the standard errors right. So now I'm going to kill myself for getting this question wrong because I don't think that's in the exam. Should I risk this? It's not in the exam. Question. You have a linear model, and you're estimating the slope parameters using OLS, and then you're estimating the same slope parameters using HLM. How would the slope estimates from OLS and HLM differ? The answer to that is, okay, you have a given regression equation. It's linear. You're estimating with OLS and you're estimating it with HLM. How do the slope estimates differ? Which ones are larger or smaller or whatever? Is my question clear? Chinwing, this is not on the exam, correct? No. Thank you. Correct.
Well, if the difference between GLS and OLS or HLM are in the errors, shouldn't the slope estimates be the same?
Catching. This is the correct answer. It shouldn't make a difference for the slope estimates.
But if it was GLS versus OLS, they would be different because you said that it built the sigma into the estimator.
It turns out the estimates will, no, the slope estimates will be the same. I mean, essentially the same. Now, a sociologist says that if you do HLM versus OLS, now suppose that the application is that you have a bunch of kids nested in classrooms, nested in schools. Again, you do OLS versus GLS, the slope estimates are basically the same, but the standard errors are different. How would they differ? Which method will likely have larger standard errors? So the assumption was I have kids nested in classrooms, nested in schools. Once I estimate with OLS, once I estimate with HLM. Which standard errors are larger? Okay, we're going to do show of hands and everybody has to say one or the other. So who thinks that the OLS standard errors are larger? Who thinks that the HLM standard errors are larger? 1, 2, 3 correct answers.
Okay.
Almost certainly. Why? Why would that be the case? All right, that's the second question. So this was 2 points, now come the 5-point questions. Why? Frankie?
We're gonna ride this success train as far as it will take us.
Yeah, we certainly will.
So they have more robust standard errors, the GLS and the HLM. And like for them to be correct, because we're gonna have to make these assumptions, which means in making those assumptions, we have to widen the errors. Should I get off the train?
Yeah.
All right. That's right, it was a fun ride.
But I feel like there are no negative points, so
I had a good
that's
time.
okay, yeah. You should try. And in all seriousness now, if you don't know the answer, you're still going to write something, right? Because you can't get less than 0 points for the answer. No? Please do that. Last time, some people just left questions blank. And you should at least try, give us your Hail Mary. Okay, so why would the HLM standard errors likely be larger? So here's the intuition. OLS assumes that, so, right, again, you have 1,000 kids in a bunch of classrooms in a bunch of schools. OLS says, wow, awesome, 1,000 independent pieces of information. It's a lot of information. HLM, however, recognizes that these kids, that once you know something about the first 20 kids in the classroom, you probably know everything there is to know about the 21st kid in the classroom. The kids in the classroom are not independent of each other. So an additional kid in the classroom doesn't give you an additional independent piece of information. So this nesting, in a way, reduces the amount of information that you have available. And that should increase the standard errors. Maybe this is easier to think through with families. Suppose you have a bunch of kids in families, and each of these families has 6 kids. Well, once you know what there is to know about the first 2 kids, you probably know what there is to know about the second, third, and fourth kid, because siblings tend to be very similar to each other. So in a way, increasing sample size by a fixed amount with nested data gives you less additional information than increasing the sample by the same size using independent information. Hence, likely the HLM standard errors are going to be larger and they're going to be correct.
So I guess my confusion comes in with the second benefit of GLS, which is that it is efficient. So like substantially, how can we think about it being efficient if it actually gives us larger standards?
Among the correct standard errors is as tight as you can get. But remember, OLS was plain wrong.
So the first advantage is that they're correct, and then they are the most efficient of the correct.
Correct.
Okay.
And right, so this is an important point. Efficient doesn't mean the smallest standard error possible. It means it's the smallest possible while still being correct. Right? Otherwise, the efficient standard error would always be 0. You know, my estimator for standard errors from now on is that the standard error is 0. Yeah, it can't get smaller than that, but almost certainly that's always wrong. Does that affect consistency? Pardon me? Does it affect consistency? Go in a linear model, going from OLS to HLM does not affect consistency. This is just about the standard errors. So now I think I need to move on. What's next? Question, is HLM only necessary for clustering? With clustering, do we always need HLM? Well, we've met HLM only for clustering. And basically, yes, you use HLM for clustered data. However, you don't always need HLM with clustered data because sometimes clustering doesn't affect the standard errors. Oh my God. Did I just say that? It is true, but it is way beyond this class. So now, why else might we do HLM? Well, because HLM gives us a really convenient way of thinking about relationships between variables at different levels. So let me lead up to that. Why under OLS are within, sorry, I just copied this question. Let me rephrase it. When are the within and between estimates the same under OLS? Well, the within and between estimates are going to be the same if the variable has a constant effect on everybody. So under the assumption, so if it is true that, say, age has the same effect on everybody, then the within estimate for age and the between estimate for age are going to be the same. That's almost never true. And then, now I'm adding something. When the between and within estimates differ, they're sometimes interpreted as the between estimate is sometimes interpreted as the effect of context. I want to review that. Okay, because I've said under which condition this makes sense and under which this condition doesn't make sense.
Can you just repeat that? You said it's called what?
So we've learned something in HLM. We can compute within and between estimates for the effect of a variable on the outcome. The within and between estimates often differ, which, if nothing else, are evidence of effect heterogeneity. But sometimes the between estimate is interpreted as the effect of context. For example, if we find that the average age of my classmates affects my achievement, then we're liable to interpret this as saying, oh, there's a peer effect. But this interpretation is fraught with danger, and you want to know why that is. Okay, new topic, limited dependent variables. From the questions, it sounds like Those are your best friends. And they are mine too. So we have met Tobit, Probit, and Logit models. Tobit, Probit, and Logit models. I've asserted at various points in the course that Probit and Logit, for all intents and purposes, are the same. In fact, they differ in only two things. They differ, let me not give you all the details. The point is, if you know the Probit estimates, you can just multiply the Probit coefficients by a known constant to get the Logit coefficients. So in that sense, whether you use Logit or Probit is really pretty much the same. But Tobit is really different. Why is Tobit different? Tobit's different because it takes different dependent variables. So we used Tobit under what circumstance? Yeah.
Use it for one-sided sensor.
For one-sided censoring. Tobit. So we need one-sided censoring. So we had point cloud. That's our regression line, but our outcome Y was censored. And what does censoring mean in contrast to truncation?
Those values above the threshold we assign to the threshold.
So if somebody had, let's the censoring threshold here be 100 and the outcome be income. If somebody has an income of 105, the data would just say 100. And we'd have a little note in the codebook that says 100 actually means 100 and above. Good. What's truncation? The data are taken out. If we truncate observations with income over 100, it means we're chucking them from the data set. Or we assign them a missing value, which is essentially the same. Good. All right. One-sided censoring. Okay, so if we have one-sided censoring, we can do Tobit. What else do we need to assume in order for Tobit to work? We had to make some assumption about the errors, right?
Yeah.
What did we assume about the errors? Okay, homoscedastic, yes. What else? Normal. We assumed that they were normal. Now the point, the way we can still get something out of Tobit is by assuming a distribution on the errors. Because that way, see in this area here where we don't have truncated data, we actually observe the entire error distribution. Down here, we can estimate the variance of the error distribution. And now, under the assumption that this variance is the same everywhere, we can go to an area where we have essentially no observations left, right? These observations here are left. These are censored. And now we can get the probability of censoring up here. Pretty good. What's more, if we know that this is a normal distribution, we can feed this into our likelihood function. So Tobit estimation is always maximum likelihood. OLS. All right. Now you want to understand under what conditions Tobit is biased and in what direction. Under which censoring conditions OLS is biased and in what direction. Specifically here, if we used OLS to fit a line through this censored point cloud, what would our regression line look like? Would it be steeper or shallower? Hands up for steeper. Hands up for shallower. Right on. So, well, S estimate would be attenuated for the true. Okay. Now, the latent variable interpretation of probit and logit extends our Tobit logit to two-sided sensor. So now we only know whether somebody's income is above or below a certain threshold, say the poverty line. In fact, we don't even need to know the exact centering threshold. We just need to assume that there is a threshold. People either fall above or below. Now, with two-sided censored data, we really have an outcome that's just binary. So we have our y is now either 0 or 1. And that's kind of weird. Now, we could run a linear probability model for the probability of an outcome equal to 1. But what are the two problems of the linear probability model? Somebody else? No, somebody who's not talking, sorry. Thank you. Somebody else. What are the two problems of the linear probability model?
Outer range predictions.
Outer range predictions is one. So we have this is y, a bunch of ones, a bunch of zeros. We fit a line through it. So we have outer range predictions. Yeah, that's nasty. What else? Okay.
So heteroscedastic.
Heteroscedastic errors. Correct. These are the two problems of the linear probability model. This out of range prediction business you can fix. How can you fix that?
So actually, you can change it to unlinear probability model.
Right. So but then you're no longer doing a linear probability model.
So you,
right?
you need to use a link function.
Okay, so you're one step ahead. I still want to stick with the linear probability model. And the point is, if you just change the functional form of your x's, you can get rid of these out of range predictions. So you can still regress the probability on some nonlinear function of the x's, get rid of the out of range predictions. How do you deal with the heteroscedastic errors? See beginning of this review. You either compute robust standard errors or use GLS. So that'd be great. Good. Okay. Now, before we go into logit and probit, I exhort you to give the linear probability model a shot, because the two problems that we've just listed have solutions that the linear probability model is way easier to interpret than the probit and the logit. Way, way easier. And if you're talking to applied economists, whenever you show a logit or a probit, they'll raise their hand and say, could you also show us the analogous linear probability model? And God help you if the results don't agree. So, but now let's estimate, let's transform our linear probability model into nonlinear probability model. Now, one general way, this is here, the next question, can you explain link function? Let me stick with this. Can you explain what a link function is? Yes, indeed I can. So I want to just revisit the issue of nonlinear models. So suppose you have y equals e to the x b. Let's suppose there's just one x variable plus e. Okay? This is not a linear model like we know it, because you've exponentiated your x's. Now, this link function business is just saying that you could take your original dependent variable and transform it through some function so that the right-hand side becomes linear. So how do you transform y so that the right-hand side becomes linear here? Take a natural log. So the natural log is now the link function that transforms y into a linear function of the xb's. Hey, that's great. Okay. Now for the logit, this is the way it goes. If you, for example, have count data, that's also what you would do. Right? If you have strict, like a count is like 0, 1, 2, 3, and so forth, can't be negative, hence it's unlikely that your errors are normally distributed because they have a bottom of 0. All right, just take the log of the counts and go about your business. Now, the issue with these 0, 1 variables in logit probit is that, of course, the predicted probability has to be between 0 and 1. So now we need to transform whatever the true regression, whatever the true data generating mechanism is, into some function that doesn't exceed 0 and 1. So we probably want some S-shaped thing. Oh, interestingly, the logit link will do that for you. So the logit of y is the natural log of p over 1 minus p, and we assume that that's linear xb into e. So now this thing here, that's a link function. So we've transformed our y, or the probability of y equals 1, to the log of p over 1 minus p, and assumed that this thing here, the log odds, are linear in the x's. This here is the log odds. Okay. So that's what the link function does. The link function just transforms your outcome so that the transformed outcome is linear in the x's. Great. Now, you could use a slightly different link and get the probit. The link function for the probit is just the cumulative density of the standard normal distribution, which, funnily enough, has essentially the same shape. But we've not dealt with that because the formula is nasty. We've just looked at the logit. Good. Now, the next question, skipping. Sorry. About the linear probability model. Somebody asked, could you explain the scale factor issue with the linear probability model? What is the scale factor issue with the linear probability model? Is there one? There's not. The linear probability model is just a linear model of the probabilities, and no scale factor issues involved. Okay, now let's interpret logistic regression. Jimmy, did you do this in section, this handout?
Who was a part of the problem set?
This is part of the this is part of the problem set. All right, so let's with the same numbers.
Yes.
Yes. Okay. Actually, no. It's we're going to redo your problem set now. Okay. So now suppose that we have a logistic regression output. Whoops. All right. So the log odds happen to be intercept of 0.2 plus coefficient of 0.2 on age minus 0.3 on race. Right. So the key thing to know is that there are essentially three metrics at which you could interpret this output. The first metric is the log odds. The second metric is the odds. And the third metric is probabilities. Good. Now, each of these three metrics deal with the probability that y is y. But of course, we're taking different functions of these probabilities. Most immediately, what Stata spits out for you are the coefficients of the logistic regression model, which do what for us? Well, they tell us how a change, say, in age affects the log odds. It's perfectly fine to look at these coefficients with two limitations. Number one, these coefficients are not identified. They're only identified up to scale. Right? That means you shouldn't compare coefficients across equations. Second problem with looking at the coefficients is people have famously poor intuition for the meaning of log odds. So suppose we're estimating income and we find that their coefficient having a PhD on the probability of being high income is 17. Is that a large effect? Looks like it, right? 17 here. Usually in logistic regressions, you never have coefficients that are larger than 2 or 3 at most. But now the coefficient of PhD in high income is 17. Well, it turns out this doesn't have to, while this looks like a large effect on the log odds, it may be a minuscule effect at the predicted probability, because perhaps the people who happen to get PhDs would be high income anyway. So their probability of being high income is, already like 0.98. And yeah, going from like a bachelor's to a PhD increases the odds of being high income by 17, but really you just get moved from probability of 0.98 to a probability of 9.85. This is entirely possible. So don't reify these coefficients. Okay, and I'm jumping ahead. So we have these three metrics: log odds, odds, okay, and probabilities. Okay. Now let's first just compute predicted values. Suppose we're interested, what was it? We're interested in predicted log odds, odds, and probability for somebody who's age 20 and his race equals 1. Maybe race here means minority. minority versus majority. So what are the predicted log odds for 0.02 plus 0.2 times 20 minus 0.3, that's 3.9, is that right? 708. Yeah, so that's 3.9. Excellent. So the log odds of being high income for a 20-year-old of race 1 are 3.9. Think on this sentence. I have no idea what this means. The log odds of being high income for somebody who's age 20 and is race 1 is 3.9. Great. If I had intuition for what this log odds scale meant, I could probably say something about this, but here I really don't. Okay. Now, what are the odds? Well, the odds are just the exponentiated log odds. And so the odds of being high income are 49 plus 4 something. So that's, I guess, better. So now I know that the probability of being high income are vastly larger than the probability of not being high income. But still in relative terms, right? And what's the predicted probability? For that, you have this formula that really wants to live prominently on your cheat sheet that just solves the odds for P. And that happens to be 1 over 1 plus the xb raised to the exponent. So that is 1 over 1 plus e to the 3.9 . Okay, now we're talking.
There should be a minus in front of the XP.
Minus, yes, of course. So now we're talking. Now we know that the sample 20-year-olds with race 1 have 98.02% probability of being high income. So for the first time in this conversation, I actually know what we're talking about. Because I can think about probabilities. I have first, but this may just be my personal limitation, okay? I have a really hard time thinking about odds and log odds, right? Like for odds, I just look whether they're greater than 1 or less than 1. Other than that, I have no intuition for the scale of probabilities. Yeah, interpret these. Yeah.
So can you interpret that as percentage points?
No. Percent. Oh, sorry. This is the percent. Oh, I see. Yes. So this tells you that in the population that is represented by your data, you would expect that 98% of the 20-year-olds of race 1 are high.
Yeah, so to add question, so basically percentage point versus percentage is all about differences between the two probabilities. So for example, one person's probability has increased from 10% to 20%. It means that this person's probability has been increased by 10% point or 100%. Does that make sense?
So this is not percentage point, this is percent.
Just 98% point to 0.2%. Yes, that is the probability. The difference between probability, percentage point, and percentage, that all that comes in when you're looking at the difference between the two probabilities.
Cool. Thank you. Oh my God. Only 10 minutes left. All right, so now let's look at the effects of variables. So we can produce effects. So let's ask, what's the effect of a 1 year increase in age of the log odds, odds, and probabilities. And the log odds metric is really easy. 1 year increase in age leads to a 0.2 increase in the log odds. This point, so log odds. The effect on the log odds, is just the coefficient. And this coefficient is also known as the log odds ratio. For reasons you've gone through in the section. So that's 0.02. The effect on the odds, let's just e to the 0.02, and what the heck was that? 1.22. You'll note that the coefficient roughly corresponds to a percentage change in the odds. But now comes the hard part, effect on probability. Probability. Here we go. Right. This is hard because, as we can see here, the effect of a 1 unit change in age is down here. It's going to have a deeply nonlinear effect on P. In this graph, you'll see immediately that the effect of a 1 year change, let's see the age, effect of a 1 year change in age will have a different effect on the probability depending on what your baseline probability is. So for a 0-year-old, a 1 year increase in age will affect the probability that they are high income. Well, by basically nothing. You go from here to here, and there's really no change in the predicted probability. Similarly, up here, if you increase if you increase age from say 40 to 41, people are high income anyway, so that doesn't change the probability much either. So the effect of a 1 year change of age on the predicted probability of the outcome is going to be largest at whatever age the probability of being high income is 0.5. Because there the slope of the predicted probabilities is largest. Here, a 1 year increase made no difference. Here, a 1 year increase made no difference. But here, a 1 year increase, a real effect. Okay. Now, how do we know where on the curve somebody is? Well, for that, you need to look at their other variables. This simple model, just their race. So their race and their age together determine where on this curve they are. Good. Okay. So now, why did I not write this out properly? Okay, so now we could compute the effect on the probability in a bunch of different ways. So first of all, we could just ask for the effect of a discrete change in age on a given individual. And how would you do that? And now, you need to holler out if I'm using different terminology. You're already like super tense because I'm definitely going to use the terminology wrong. No, he's right. He's excellent. So discrete change just says, hey, for a given person I, compute I's probability when they have, whatever your x value is plus 1 minus the probability if they just have x. So let's compute the probability of being high income for somebody of race 1 and age 20, and the probability of being high income for somebody who is race 1 in age 20. So to do that, you need to use this formula. You compute the probability when the person is 20 and the probability when the person is 21. And you take the difference. Did we call this the marginal effect?
A
Did
different.
we use the partial change for the marginal effect?
We did
Oh.
have the words marginal effect on our problem set.
Oh, what?
We had the words marginal effect on our problem set.
Different for different interpretation. For different interpretation.
Different. Never mind that. Okay, so discrete change. This is for an individual. The discrete change of a 1 year increase in age on the probability will differ across individuals. So it's going to be a really, really messy summary. This is the effect of a 1 year increase in age is no longer a constant for people. So what do? We could ask the computer to compute this discrete change for every individual, and then just take the average of that. There you go. That is your average marginal effect. The point of the average marginal effect is that it gives you the effect of a covariate on the probability of the outcome with just a single number. The truth is, though, that the average marginal effect tends to be very closely related to the coefficient of this variable in the linear probability model, which once again suggests that perhaps you should just estimate a linear probability model. Now, we also had partial change. The partial change is defined as pi 1 minus pi times the coefficient on x. The discrete change and the partial change are very closely related. The discrete change says, hey, what is the change in the probability, say from x equals 15 to h equals 16, and that's this here. This is the discrete change. The partial change, and here comes a little bit of calculus, of an increase in age is just the slope of this S-shaped curve at age 15. The partial change tends to be a little smaller than the discrete change in the top. But not in the bottom of the distribution. Usually they're really quite similar, so we're not going to get excited about the difference. Now this partial change here could also be computed at different values of the probability, and each individual in the data is going to have a different baseline probability. So you take the average of that, and again, you essentially get the average margin. So let me back out here. When interpreting logistic regression, when we estimate logistic regression, we use the link function to turn the probability of the outcome into a linear function of something. This link function is the logit. The logit has the beautiful property that you can now estimate coefficients that have, an additive effect on the log odds, just like in OLS. The massive disadvantage of doing that of summarizing the effect of a covariate on the log odds with a single number are two. First, these coefficients are only identified up to scale. Second, most people don't have intuition for log odds. So we transform the log odds back into probabilities, and now we can estimate the effect of a 1 unit change in a covariate on the predicted probability. But now every individual is going to have a different effect of that covariate. So what's the advantage of having done that? Well, we're now looking at the effect on the scale that we can interpret, probability scale, but the disadvantage is that every individual has a different effect on that scale. So we take one more step, and now we're asking about the average effect of a 1 unit change in your covariate on the predicted probability across everybody in your sample. That's your average margin effect, which again summarize the effect of a unit change in your covariate on the probability with just a single number. A single number, however, which you now know probably doesn't apply to any single individual because it is an average. Okay. I guess the last question, I'm sorry about this, guys, I did not time this properly, but I think there's really only 3 questions left. What's this interaction business? So this interaction business, interactions in logic are really, really hard to interpret, but I think if you get the basics, the basic intuition for what the problem is, then you'll be fine. And here's the issue. Whether 2 variables interact with each other is always a question of the scale on which you measure them. By simply transforming your outcome, you can produce or remove interactions. And I want to show you that by looking at quadratic forms. So suppose again that, suppose that you have an outcome y that looks like this. So y, this is probably log linear in x, but if you squint, you could think maybe this is a quadratic. All right, so what does that mean? This means that y is probably a function of x and x squared. And x squared, that's sort of like an interaction, isn't it? Because x squared is x times x. X times x. Okay. Now let's transform our outcome. Let's take the log of this. Now suddenly, the log of y relates to x in a linear fashion. So now the log of y is just x times c1 plus u. This is linear, there's no interaction. So this model here, you could include x squared here, but the coefficient would be 0. So simply by transforming my outcome scale, I've gone from a model with this interaction to a model without an interaction. See this analogy? The thing with logit is that when we take the log odds and we transform them into probabilities, we're changing the scale of the outcome. Therefore, it shouldn't be surprising that 2 variables that interact on the log odds scale may not interact on the probability scale, and vice versa. In fact, sorry, not in fact. So when you're looking at a logistic regression equation, something like, so the log odds P1 minus P, perhaps they're, age B plus race B2 plus age times race B3. If B3 is large and positive on the log odds scale, this does not imply that the interaction effect B3 would be positive, negative, or 0 on the probability scale. It just doesn't follow. So inspecting the regression, if you have a logistic regression output with a statistically significant, say, positive interaction, then this does not imply anything about how this interaction term would affect the predicted probabilities. The interaction on the predicted probabilities scale could be positive, negative, statistically significant, not statistically significant. You simply don't know. You have to compute it. And that is another excellent reason to eschew the logit model if you have interactions in your model, because they're just so hard to interpret and they're often misinterpreted. So the lecture slides have some math from A. Norton on why this is the case. I think I'm kind of enamored of my little explanation here, so why don't you remember that? I'm going to race really through other stuff. Somebody asked about Wright's rule with non-standardized variables. You know what? Don't worry about that for the exam. You need to know Wright's rules, but you're going to have standardized variables. Instrumental variables. What about the stuff we did on Tuesday? Fun fact, it's not on the exam. What is classical measurement error? Independent measurement error is essentially classical measurement error. For the rest, see the slides or alternatives. One question was, I'm a little fuzzy on omitted variable bias measurement error. What are the consequences? Please look at the slides. Here's a great question, but it's not relevant for the exam. You know, maybe we're done after all. Good. Thank you, everybody. I'm going to hang out here for another minute, and then Anna,